lesson 35 of year 2 of the science class. This is the last class, and we are going to do presentations from everyone, okay, that we can. And Annika is going to start first, okay? Let's see. So I have here the presentation. Let's see. I don't know how do you put it in presentation mode. Let me see if I can. You present. Okay. This is it. All right, Annika, go ahead.
Okay, can everybody hear me?
Yeah.
Okay, so I've always loved leaves, and I've always like wanted to know more about it, and this gave me the opportunity to do that. I decided I was going to do how to identify the leaves, and well, you can go to the next slide. I don't know exactly how I should tell you.
Just say next.
Okay. So, an oak leaf comes from, like you can see, the genus Quercus, which is Latin for oak tree, and it's native to the northern hemisphere, like the U.S., Canada, and Mexico-ish. It's deciduous, and it can also be evergreen, depending on what type of tree it is. They are arranged spirally on the tree, and they're like smooth on the edges. I have a list, a whole bunch of them. Then next. Okay, this is the Sumac. It's also native to North America. It's deciduous, which means that it changes color and drops its leaf during the winter. They're kind of funky shaped, but they really are. A lot of people like to have it for fall foliage. The picture that's right, like the biggest one, is the tiger's eye, I think. I really like that they have such cool names for them. Next. Okay, these are ivy. They're from the genus Hedera. They're common wherever. I know when we first moved into our house in New Hampshire, our neighbors came over with a giant ivy plant, and I think it's still alive. They live for like forever, and certain types you can do anything to it and it'll still be there. They can be deciduous and they can be evergreen. They kind of look like a lance. They grow on everything by sticking their roots, kind of like suction cups, to walls and things. Next. All right, the other side of the leaf, or in other words, the nasty twins of the ones I just talked about. Poison ivy, poison sumac, and poison oak. Leaflets of 3, leave me be. That goes for everything but the poison sumac. Poison oak and poison ivy always grow in leaflets of 3. I'll talk about that in a second. Poison sumac grows in leaflets of 7 or 13. Either way, it's always odd.
Prime number. Mm-hmm.
Yep. Okay, next. Poison oak leaves are from the genus Toxicodendron. They're native to western North America, so like out west. They are deciduous, so they change color and die. They grow in leaflets of 3. There's 2 off the sides, and then there's 1 out in the middle, and it's always on a shorter stalk. The biggest leaflet points straight out. They aren't very tall, but they look like oak. Next. Poison sumac leaves. I didn't really talk about this on the harmless sumac, but the harmless sumac has like the pointy, really super thin leaves, and it has red furry berries. The poison sumac has white or light green shiny berries. Poison sumac is from the same genus, first name as poison oak. It's Toxicodendron, but this one is in the family Vernix. They are native to the eastern United States. They are deciduous as well, so they also turn beautiful during the fall. They are in 7 to 13 leaflets, like I said, and the same thing on these. The last one is always on a separate stalk, like on a shorter stalk. They have reddish stems, so if you look and see, there's a lot of different things that you can see in there that's different from normal. These actually grow really huge. They can be 20 feet tall. They are more allergenic than poison ivy and poison oak simply because they have more of the toxin. Next. Poison ivy is also from Toxicodendron. It's native to the eastern U.S. and part of Canada. It's deciduous. It also has the shorter stalk on the last one. It grows in leaflets of 3. And is the most common on the edges of highways and stuff because it likes carbon dioxide and carbon monoxide from the exhaust from cars. Next, as does the other ones too. What is the biggest difference between the harmless and the poison versions? It's the Urushiol. The Urushiol is an oily organic allergen that's in the stalks, the leaves, and the on the surface. It's in plants from Anacardiaceae. It contaminates, it's in actually a lot of different things. You can see in the bottom corner. It's in the Rangus tree. It's in the ginkgo tree. It's in poison oak and poison sumac and poison ivy. It's in cashew nut shell oil. It's in India marking nut tree, and in the Japanese lacquer tree. So there's a lot of different things that it's in, but some of them we don't even know. Like I eat mango all the time. Okay, guys, don't double check and make sure before you touch even a dead plant because it can last from 1 to 5 years, just the Urushiol. So you can touch it, even if it's a dead plant, and you'll get poison ivy, poison oak, or poison sumac. The worst is actually if you burn it. Bad idea. Don't do that. Because it can get, the Urushiol travels on the particles of the air and can get inside of you and give you the same reaction inside on the tissues in your throat and stomach and stuff. That's even worse than having it on you outside. Just saying. I actually have not I have not gotten poison ivy or anything. So I don't know if I'm allergic to it. But and because of that I may not because if I live right, just a minute, I'm teaching, okay. If I live to adulthood without getting contaminated, without having a reaction to poison ivy, I have a 50% chance that I never will react to it. It's been found that people who are with each contact, the time period between contact and the breakout gets shorter. So like if you get it the first time, it's likely 7 to 10 days after you actually touch it that you'll get a rash. Each time you touch it and get a rash, it'll be shorter time. And the more you have the reaction, the worse it'll be. No, it is not an immediate reaction. If you are allergic to it, you're more likely to be allergic to tree nuts, to cashews, and to mango, because those foods contain it.
Wow. Very interesting. Mm-hmm.
I was gonna say one more thing. Oh, I didn't put any pictures of the rash because I didn't like looking at them myself, but it it doesn't look pretty. My dad actually got it one time and couldn't figure out what was wrong with him, and then decided he was going to look it up, and that was what it was. I did actually add a sort of a gospel principle. That's the last slide if you want to turn that one on.
Yes, Oh, beautiful. Mm-hmm.
I love that quote. I can't tell you where it's from because I don't remember, but it's true. And if we, just like poison ivy and poison sumac and poison oak versus the non-hazardous versions, we can grow something in our brains with our thoughts that could possibly be poisonous to us. And we need to be careful what seeds we plant, because some people on accident actually, poison sumac is the one that does it the most. They sell sumac, the non-hazardous one, for people who are landscaping, so that because they like it for the fall foliage. Yeah.
Yeah. Wow.
And some people accidentally do the poison version. So it's important to watch what we grow, watch what seeds we have. And that's it.
That's great. Wow. This was very, very interesting. Thank you so much. What an interesting presentation, really. Do you know here in the chemical composition what the R is for? I do know that in organic chemistry, whenever you have a chemical, represented this way, these intersections here, actually, the intersections on this hexagon are all carbon. Okay, so there's 6 carbon atoms that are joined together. So they should have a C there, but normally, because a lot of all the organic things have a carbon in it, they don't represent it. They just put what is on the extremities of the molecule. Okay. So does that make sense? Mm-hmm.
Yeah. The R, I read about it, but I don't remember exactly what it actually stands for. I do know that each, when you look, like the top picture, when you, poison oak and poison ivy and poison sumac all have it, but they all have a different variation of it. And that is signified by a little number, like a 1 or 2.
Yeah, one atom or 2 atoms of that.
Yeah.
Mm-hmm. Yeah, I think if I'm correct, okay, let's see if we can go to that really fast. Okay, I think that they are, so yeah, here you have all the things. Okay, I think that the R is radon, but I don't remember now. Mm-hmm. Okay. All right. Okay, excellent. Well, Mac, are you ready for your presentation? You are next. Annika, very, very good. Very, very nice.
Okay. All right, can you hear me?
Loud
all
and
right,
clear.
so this is my, yeah, all right. So this is my science presentation, and if you go to the next slide, please. The next slide. Okay, it's about galaxies. So there are 3 different types of galaxies: the elliptical galaxy, the spiral galaxy, and the regular galaxy. All right, just go to the next one. Let's start with the elliptical galaxy. It's not that good of a picture, but I don't know. I guess it's because of the pictures I found online. Anyways, the elliptical galaxy is kind of in the shape of a sphere. It is 3-dimensional without much structure, and its stars are in somewhat random orbits around the center. Most elliptical galaxies are composed of the remains of deceased stars. Elliptical galaxies are usually found in the most violent places of the universe. If you go to the next slide. Like at the heart of galaxy clusters and in compact groups of galaxies. So, as you can see in this picture, those kind of yellowish, orangish dots you see, those would be the elliptical galaxies. All the other ones, the purple ones, green ones, red ones, all those are other different galaxies, and I'm pretty sure it's a real picture. So, all right, go to the next slide. All right, now we're going to talk about the spiral galaxy. All right, go to the next slide. All right, the spiral galaxy has 3 main components: a bulge, a disk, and a halo. The bulge is a spherical structure found in the center of the galaxy, and it contains older stars. The disk, also known as the arms of the galaxy, is made up of dust, gases, and younger stars. Our solar system is also found in the disk or arms of the Milky Way. So if you look at the picture, the solar system kind of design on the left, if you look at one of the arms, I don't know if it's I don't know if this is an actual picture of our Milky Way galaxy, but in one of the but if it were, our solar system would be one of those tiny little dots in the little arms there. So that's that just proves how big our galaxy is compared to some other ones.
Yeah, our sun is on one of the arms, one of the outside arms of the galaxy. And actually, in this picture, a dot would probably be a cluster of stars. Okay.
Yeah. All right. And what else? All right, the irregular galaxy. Irregular galaxies have no regular or symmetrical structure. Collectively, they are thought to make up about a quarter of all galaxies. Some irregular galaxies. Here, go back to the next one. To the left. There you go. Back to the left. Back. Right there. Right there. Irregular galaxies. Okay. So yeah, they make up about a quarter of all galaxies, and some irregular galaxies were once spiral or elliptical galaxies, but were deformed by disorders in gravitational pull. So you can't really tell with this one because it's kind of been pulled apart. So you can go to the next one again now. That one, you can tell it's been kind of pulled apart. Well, kind of. It doesn't really look like anything much, but it says it used to be an elliptical galaxy or a spiral galaxy that was pulled apart by just like gravity around it. Anyways, irregular galaxies may contain abundant amounts of gas, dust, making it almost impossible to see the surrounding stars on the planet. So as you can see, I've placed question marks in those little corners there to prove that you can't really see the stars behind it because of how much dust and debris there is. Alright, so go to the next one. Alright, now we're going to talk about the characteristics of galaxies. Since I've gave a brief explanation of each of the three main galaxies, we're going to talk about the characteristics. Alright, so spiral galaxies can actually move. They move through the universe because they kind of act like a propeller, as you can see in this page. Because in the center of each spiral galaxy, there's a supermassive black hole. And basically what that does, it spins the entire galaxy, and it usually takes, like, depending on the strength or the size of the galaxy, or the strength of the super black hole, it can take up to like 5 billion years to make one revolution. So it takes a long time, but it slowly but surely it makes its way through the universe. Also, if you go to the next slide, please. Alright, the Andromeda Galaxy is actually coming this way. It actually will eventually hit the Milky Way, and some scientists predict total chaos, while others think that the planets will be so far apart, and there will be so much space in between the planets and stars that it probably won't be that chaotic. Anyway, so
that is something important to understand, is that even though these pictures of galaxies, they look like one thing, you know, there's so much empty space in between them that you certainly have times when two galaxies run into each other and they basically just run by each other, okay, run through each other.
Yeah,
the gravitational pull affects the movement of the object, but it's not that there are sure collisions at all.
Yeah, I mean, there will be some collisions, no doubt about that, because, I mean, some gravitational forces will be thrown apart and stuff, but other than that, it probably won't be that chaotic. Anyways, so now I'm going to talk about quasars. I actually have a link to a video here that will explain quasars, and then I will be explaining this after the video. So if you could follow the link.
Okay.
And then go to full screen.
Okay. Okay, let's see. The ad coming, ending soon. All right. There we go. Can you hear?
Astronomers using the European Southern Observatory have found a quasar that's more than 5 times more powerful than any previously seen. Astronomers on Earth first became aware that quasars existed in the 1950s. Back then, the term quasar meant quasi-stellar radio source because they looked like very bright points on the sky at radio frequencies. Now, we've come to understand that they are actually gargantuan sprays of matter and energy powered by supermassive black holes in the centers of some galaxies. Wait, here he says, don't black holes suck matter in? Well, sure they do, but as they do, they tend to shred that matter apart, spinning it up, forcing it outward at very high speeds. Researchers have cataloged more than 200,000 of these objects. The very nearest one is more than 600 million light years away from Earth, and most are at least 3 billion light years back in space-time. But this discovery is the first to confirm the theorists' prediction that these cosmic vortexes could truly be this hot, this bright. For Space.com, I'm Dave Brody.
Alright, that should be the end of the video right there.
Mm-hmm.
Alright, so
Excellent.
I don't know if you guys got the audio that well, but basically, just a quick explanation of what he said. It's in the center of of super black holes or black holes. Sometimes maybe in the center of our spiral galaxies where the black holes are. They suck up so much stuff and they shred it all up till they can't have anymore, and they shoot it out in 2 lasers of energy on each side, as you can see in that picture. So, anyways, that's that. So, does anyone have any questions? I know in the comments, people were asking when this when the Andromeda Galaxy was going to hit us, and I believe it was like 2.5 billion years. So we don't have to worry about it. We don't have to worry about it at all. We don't have to worry about it in our lifetime. So, anyways, if we go to the next slide, that's just basically my way of saying thanks for paying attention.
Thank you very much. That was a
Yeah.
great presentation.
Yeah.
Really appreciate it.
All right.
Okay, any
Thank you.
questions, guys?
Any questions?
Any questions? Okay. So let's see. Now we are going to go. Who's next on the docket? Okay. Let's see. Who do we have next? I think that is Macy or Christopher. Mm-hmm. Okay, Christopher. All right, and I have your presentation also here. Okay. Excellent. Wow. Okay. All right. Very good presentation. Okay, Christopher, your phone is muted. Okay, so you need to unmute yourself so we can hear you. Okay, there you go.
All right. Can you hear me now?
We can hear you. Little
Okay.
faint. Okay, there you go. Much better.
All right. So, yeah, my presentation is about megathrust earthquakes. So, next slide. So, these earthquakes are basically like the most violent, deadly earthquakes that happen in the world, and usually they're the ones that are above like 9.0 magnitude. And so I have a little diagram there of basically how it works. And the 4 most destructive earthquakes in history, like ever since they started recording, all of them were megathrust earthquakes.
Mm-hmm.
And they usually have tsunamis accompanying them. So, all right, next slide. So, number 1 is the Valdivia, Chile earthquake in 1960, and it was the most powerful earthquake ever recorded at 9.5 magnitude. And so I have a diagram in a few next slides. You'll probably see it, but almost a quarter of all earthquake energy released in an entire century, from like 1900 to 2000, was concentrated in the Valdivia earthquake alone. So, like a ton of energy was released in that earthquake. And even though it was such a strong earthquake, only about 6,000 people died, which was extremely low for such a huge earthquake.
Yeah, amazing.
Yeah, and the earthquake triggered a bunch of other things like landslides, tsunamis, floods, and actually even a volcano, because all the tremors activated a volcano. So, all right, next slide. And the tsunami that was accompanying it was extremely powerful, and it affected countries like Chile, Hawaii, California, even like Japan and Alaska. And so that picture right there shows travel times of the tsunami. And you could see some pictures of Japan and Hawaii. So that was really strong to reach all the way over there. All right, next slide.
It is amazing. Think about the speed at which this travel. Okay.
Oh yeah.
The speed and the energy of this wave. Amazing, really. Amazing.
And see, if you go back, just one side.
Hold on, sorry. This one?
Then you can see at Hawaii that there's actually a parking meter right there, and the tsunami just totally like bent it up.
Yeah.
All right, so next slide, yeah. So number 2 is the Great Alaskan Earthquake in 1964. And it was the second most powerful earthquake in the world at 9.3 magnitude. And so it was so strong that shocks like skyscrapers in Houston actually swayed because it was so strong. And the vertical displacement, like how much the ground lifted up and also sank, was up to 38 feet. And like as you can see in that picture right there, like in the 4th Avenue, you can see that that little part kind of collapsed right there. And actually, I wish my dad was actually here because he was, let's see, like 5 years old when this happened. So.
Wow.
Yeah, and he said that like he looked out the window and he could see the street just basically like going up and down in a wave, sort of. So it's just like that's crazy. Yeah.
Where was he when this happened?
He was in Anchorage, but I think he was in one of the neighborhoods that wasn't really as affected because his house actually only had like a few cracks in it, and it was like fine. So he says that he thinks that they were protected because, and I think this too, because he said that their whole family, they actually gathered in the living room and they were praying. So.
Holy cow.
Yeah.
That's one of those things that you don't forget.
Yeah.
If you're 5.
Yeah, he was only like 5, but he still remembers it perfectly. All right, next slide. And so the tsunami that resulted from this was also extremely powerful. And as you can see in that picture, it just drove a 2x6 plank right straight through a tire. And the earthquake actually, as well as having the main tsunami that traveled across the ocean, it also made like 20 smaller tsunamis that were because landslides under the ocean, they displaced large amounts of water.
Wow.
Yeah. And they even had a few waves in Antarctica.
Oh my goodness.
All right, next slide. So a more recent earthquake was the 2004 Indian Ocean earthquake and the tsunami, because the tsunami was actually the more deadly part of it. But as you can see in that chart there, like I mentioned before, it shows Chile in light blue, and you can see that it released almost a quarter of all seismic moment release. So,
Mm-hmm.
and then Sumatra is at the top right there. And so it was the third.
That's this one. Mm-hmm. Yeah.
Yeah. So it was the third largest earthquake in the world at 9.1 magnitude, and it was felt in countries all around it, like Bangladesh, India, Malaysia, and Singapore, and all that. They actually had recorded vertical movement in Oklahoma.
Mm-hmm.
And I think the reason for that is because a bunch of seismic waves, they also travel through the mantle, so they probably came out there too. And so I got some numbers right there, and I thought it was really amazing. Like the energy release was equivalent to 26 megatons of TNT, and about 1,500 times the energy released in the Hiroshima atomic bomb.
Mm-hmm. I remember this one clearly, and I have a friend of mine that works for the church in the welfare department, and he was sent to Sri Lanka, okay, to help with the welfare recovery for the people there in Sri Lanka and in Myanmar. Okay, that were the places most affected really by this earthquake. Mm-hmm.
Yeah, and also the earthquake was so strong that it actually made the earth kind of wobble a little bit, and because of that, it made the earth spin just a little bit faster, so it shortened the day length by about almost 3 microseconds. So.
Mm-hmm.
Which is not very much, but still it's incredible, yeah.
Mm-hmm. Yeah. Mm-hmm.
And so also, yeah, next slide.
Mm-hmm.
Yeah. So then you have the tsunami, which was actually the worst in all of recorded history. And so it affected countries like in the picture at the bottom, all around the Indian Ocean, even all the way to South Africa, which was quite interesting.
Yeah. Mm-hmm.
And then I also have a picture of that right there in Thailand, and I thought that was a really cool picture. Like whoever did that caught it almost perfectly. And you can see like a tourist right there. He's just kind of standing there, almost confused or something, you know.
Yeah. This tsunami was actually also very deadly. There were a lot of people that died because before the tsunami hit, the water kind of emptied from the beach, okay, or here in the coast of Indonesia, the island of Sumatra. And so people were going to the beach to see what was going on and everything instead of going up to the mountains, and they got caught. Mm-hmm.
Yeah. All right, so next slide. And so now one that was really recent is the Tohoku, Japan earthquake. And that one, like everyone heard about that one. And I remember in the lesson before that we watched like that documentary, like you included that documentary. And so, yeah, it said that because of social media, it was all over, like everywhere. And it was at 9.0 magnitude, so it was the 4th largest earthquake.
Mm.
And it was the largest in Japan. And also the numbers there are really cool. Like the whole of Japan shifted like 8 feet closer to North America, and then parts of it dropped about 2 feet. And then the seabed next to it, it moved 50 meters southeast. So while Japan moved, west, then the seabed slipped southeast. So. And then in that one also, they found that the speed of the Earth's rotation increased, so the day also shortened by 1.8 microseconds, and the entire Earth shifted 4 to 10 inches off its axis. And when I heard that, I was just like, that's just crazy.
Wow.
And then seismic waves. I saw that, and it caused an ice stream, the Williams ice stream, to slip 1.5 feet all the way in Antarctica. And if the energy that was released in that earthquake, if it was harnessed, it could power a city like Los Angeles for an entire year. So, next slide. And so then the resulting tsunami, like I have a picture right there, which is also an amazing picture of it pouring over one of those seawalls. And in Japan, they were actually quite prepared for an incident like this. Like they had seawalls, they had tsunami drills and everything, but it took them quite by surprise because it was so big. So it just completely went all the way over their walls. And they also had waves in Hawaii and all along the western Pacific coast, like Alaska and Chile, like it shows in that diagram right there. And like it also damaged the Fukushima Daiichi nuclear power plant. And so then that resulted in one of the largest nuclear incidents ever since Chernobyl. And they still have it offline, and they're still cleaning it up because it was really big. So.
But interestingly enough, no one died out of this nuclear incident.
Yeah, and then
okay.
Yeah, thankfully, yeah.
Yeah, so thankfully, so all the safety features and everything, they actually worked.
Yeah. All right. So next slide. And so then they've been thinking and like writing articles about possible megathrust earthquakes in the future. And so one of the areas that is actually one of the most likely to have an earthquake like that is in the Cascadia subduction region, which is about where the Juan de Fuca plate, where it subducts underneath the North American plate. And so that right there, that's a potential area where it could build up stress, like in the diagram at the very beginning. And actually the last earthquake there was in 1700, so that's quite a lot of time for build-up energy. So they're thinking that maybe they should take a lot of precautions over there, because that could affect quite a few cities.
Yeah. Very close to the coast also, yeah.
Yeah, and I think that's the last slide.
Okay. Excellent. Wow, very nice. Quoted with all the sources and everything. Very, very good. Excellent presentation, Christopher. Good and very, very informative. I really like how you went through everything and really did some research on each one of these earthquakes. So
yeah, I think earthquakes is a cool subject. Like it's actually pretty scary, but still, yeah, it's cool.
Yeah, yeah, it's certainly something very interesting to study.
Yeah.
Very, very good. Okay. Yeah, another standing ovation here. Okay, Macy, now I'm going to share the screen, change to give you control of the screen, okay? So you need to kind of accept that and go ahead and take us to your presentation.
Can you guys see my screen? Okay, so I don't know if my screen includes like the chat bar and Mr. Ribaldi's webcam, because for my screen,
yeah, when you share your screen, you just see your screen, okay? So don't worry.
Yeah. So I'm wondering, can you guys see Never mind. Sorry, dumb question. Okay, so my presentation today, I'm going to be talking about Pluto. When I was a little tiny kid and I first learned from my mom that scientists had decided that Pluto wasn't one of the planets, I actually cried. And I was really sad. And I don't really remember why I was so sad, but I was just so depressed that Pluto didn't get to be a planet anymore. Because I just thought of it being super sad. Okay, so, anyways, sorry. By the way, if you hear the noise of a bird, that's my phone. I don't have, like, a bird trapped in my bedroom. Okay, so Pluto. It is the second most massive dwarf planet after Eris. It's the largest object in the Kuiper belt and possibly the largest known trans-Neptunian object. Now, when I first read this part, this is a Wikipedia article, I had no idea what trans-Neptunian meant. So over here, I just looked it up. And so basically it says a trans-Neptunian object, or a TNO, is any minor planet in the solar system that orbits around the sun at a greater average distance than Neptune. So that's basically it. Okay. Also, it is the 10th most massive known body directly orbiting the sun. Like any other Kuiper belt object, Pluto is primarily made out of rock and ice, and it's relatively small. It's about a sixth the size of the Moon, and sort of a third its volume. It has an eccentric and highly inclined orbit that takes it from 30 to 49 astronomical units. That's what AU stands for. So that's like 4 to 7 billion kilometers from the sun. Hence, Pluto periodically comes closer to the sun than Neptune, but its orbital resonance with Neptune prevents the bodies from colliding, which I thought was kind of interesting. In 2014, it was 32.6 astronomical units from the sun. Light from the sun, I thought this was super crazy. Light from the sun takes about 5.5 hours to reach Pluto at its average distance, which is about 40 astronomical units away. So Pluto was discovered in 1930, and it was originally considered to be the 9th planet from the sun. Its status as a major planet fell into question following further study of it with and the outer solar system over the next 75 years. Because starting in 1977, there were being discovered a lot more different planetoids and dwarf planets and other things like that, like the minor planet Chiron and a bunch of other, it says, numerous icy objects similar to Pluto that also had eccentric orbits. The scattered disk object called Eris, discovered in 2005, is 25% bigger than Pluto. So I don't know, I feel like it wouldn't really make sense to call Pluto a planet, but then not also call Eris a planet if we're just going by size, you know? So, the understanding that Pluto is only one of several large icy bodies in the outer solar system prompted the International Astronomical Union, or the IAU, to formally define planet in 2006. This definition excluded Pluto and reclassified it as a dwarf planet, and specifically as a Plutoid. Astronomers who oppose this decision hold that Pluto should have remained classified as a planet, and that other dwarf planets and even moons should be added to the list of planets along with Pluto, which I think would be a bad idea, because then, I mean, for centuries and centuries, we've just had these planets that all have meanings behind their names and all these kinds of things. So Pluto was just kind of the extra little kid at the end who was different, and I don't know where I'm going with this. Sorry, tangent. So, well, I think we should just stick to the 8 planets left. Pluto has 5 known moons. There's Charon, who's the largest, he is just over half the size of Pluto. There's Nix, there's Hydra, Kerberos, and Styx. Pluto and Charon are sometimes described as a binary system because the barycenter of their orbits does not lie within either body. The IAU has yet to formalize a definition for binary dwarf planets, and Charon is officially classified as a moon of Pluto. Oh, this is going to be cool. Okay, so on July 14th of this year, the Pluto system is due to be visited by spacecraft for the first time. Woohoo! It says the New Horizons probe will perform a flyby, and they will attempt to take a bunch of measurements and pictures of Pluto and its moons. Afterwards, the probe might visit other stuff that's in the Kuiper belt. So I thought that would be really awesome.
That will be interesting to pay attention to. It's coming up just in a couple of months. Mm-hmm.
Yeah.
Yeah.
So the discovery of Pluto. Okay, so in the 1840s, using Newtonian mechanics, Urban Lee Verrier predicted the position of the then undiscovered planet Neptune after analyzing perturbations in the orbit of Uranus. Subsequent observations of Neptune in the late 19th century caused astronomers to speculate that Uranus's orbit was being distributed by another planet besides Neptune. In 1906, Percival Lowell, he was a wealthy Bostonian who founded the Lowell Observatory in Arizona, started an expensive project in search for a possible 9th planet, which he named Planet X. By 1909, Lowell and William H. Pickering had suggested several possible celestial coordinates for such a planet. Lowell and his observatory conducted his search until his death in 1916, but to no avail. So he just couldn't find it. Unknown to Lowell, on the 19th of March in 1915, surveys had captured 2 faint images of Pluto. But they weren't recognized for what they were. So I've got a picture over here. So you can see right there and right there is the 2 pictures. So there are 15 other known pre-discoveries, with the oldest made by the Yerkes Observatory in August of 1909. So, because of a 10-year legal battle with Constance Lowell, Percival's widow, who attempted to wrest the observatory's $1 million portion of his legacy for herself, the search for Planet X didn't resume until 1929, when its director, Vesto Melvin Slipher, which I think has a really funny name, summarily handed the job of locating Planet X to Clyde Tombaugh, a 23-year-old Kansan who had just arrived at the Lowell Observatory after Slipher had been impressed by a sample of his astronomical drawings. So it was Tombaugh's job to try to search the night skies and find it.
That is interesting. We will have to probably keep it to a shorter version, okay? Because I really want to have Alex do his presentation. But it is really interesting that most likely Pluto was discovered really because of this very concentrated effort by the scientists to look for it. You know,
Yeah.
and it is interesting that they really were looking for something that theoretically should have been there by measuring the disturbances of the orbits of Uranus and Neptune.
Yeah.
It's a great story, really, because imagine like you mentioned before, there are other objects that are more massive, and if they would have been closer to Uranus and Neptune and disturbed their orbits, okay, they would have been, you know, looking for that instead.
Yeah.
Yeah. Yes, a lot of math to calculate that.
Yeah.
That is interesting. Good.
Oh, that's all I've got. So.
Okay. Well, no, actually, you have a lot more that I could tell, and thank you for putting all this together. That was actually very, very interesting on the discovery of Pluto and the history of this now dwarf planet.
Yeah.
So, all right. Any questions, guys, for Macy? Anything else that you would like to add?
Thanks, Sam.
Okay. So, Alex, you are next. Did you send me the presentation, or do you have it to present? I don't remember. I'm changing. Let's see. It was. Okay. Yeah. So you have the presentation. Alex, go for it. Okay, you are muted, so if you can unmute your microphone, then we can hear you.
Yeah, I didn't really get much stuff done because the first one got deleted, and that was just recently, and I was trying to put it back together.
Yeah, this is the case of the computer ate my homework.
Yeah, pretty much.
The new version of things now. But show us what you have, and let's talk through it. So I did make you the presenter, so go ahead and you can share your screen and show what you have. Okay.
All right, so I was just kind of doing some stuff with plate tectonics and volcanoes, all that stuff. Yeah, there's what I have right now. It's not much. Yeah.
What have you learned about plate tectonics by gathering this the things for this presentation?
Well, it's I don't know. I've always liked geology, and I took one of those video college courses, things about it, and talked a bit about oil and stuff. I really want to talk about volcanoes. Is that okay?
That is great.
Anyone opposed to that? All right.
Hey, we have had tsunamis and earthquakes, okay, colliding galaxies. Now we need some volcanoes and poison plants, okay. So this is in keeping with the topic.
Okay. So there are 3 kinds of different volcanoes. There's the shield volcano, that's all flat. There's the cinder cone, and what's the other one called? Is it like a, hang on.
You have stratovolcanoes. Mm-hmm.
Yeah, that. And shield volcanoes are usually, they usually erupt with a real thin, flowy lava, and that just kind of, it's a bit like water, or more like unset jello. Eh? I don't know. And they don't really have very violent eruptions. It just kind of flows out.
Mm-hmm.
And then there are some other volcanoes where it flies out a bit, and the more cone-shaped volcanoes. That's how you get those. And then there are the really big ones, like, you know how Yellowstone's a big, huge volcano?
Mm-hmm.
With that's got really thick, viscous lava, and it traps a whole bunch of air bubbles and everything, so when those erupt, they go boom. They go like boom.
Yeah, very explosive, those ones.
Yes,
Mm-hmm.
extremely so.
Yeah. Mm-hmm.
Super volcanoes.
Mm-hmm.
Yeah, it says here Yellowstone.
Mm-hmm.
And volcanoes usually form at the edges of the plates and stuff. The ring of fire and all that. Yeah.
Okay.
So a volcano has, it's got the big huge magma chamber. Yeah, let me click on that. Okay, it's got this big huge magma chamber down there. Some of the really big ones lead all the way down to the mantle. And it's got these different vents out in places, like there's one, there's one. And that can form different peaks of the volcano. And well, Hawaii is over a hot spot, and that when the plates move, the volcano moves along with the plates, so it just makes a big long chain of volcanoes.
Mm-hmm.
Yeah, that's what Hawaii is.
Yeah. Okay.
You know, I don't really have much more than that. I don't really have much more than that.
Just in the interest of time, we'll call it. Okay, but thank you so much for preparing. I know that it has been kind of a last-minute preparation for you, so I appreciate your courage to actually go for it. Okay. So, well, guys, thank you everyone for participating on your great efforts in preparing presentations and everything. I'm going to be working still very much trying to finish the final. So Mr. Anderson sent a message saying that we will have the finals before this Friday, and you have until June 12th to finish the final, okay? So, and I really encourage all of you to take the final, mostly just to assess your own learning, okay? Assess your progress in these topics, all right? So, thank you very much. And if I don't see you, have a great, great summer. And I hope that I'll see you again in class next year, okay? So we would like to finish with a prayer. Nicola, are you there? Would you like to offer a prayer for us? Okay, or someone that you would like to say a prayer, that would be great.
Can you hear me?
Yes, go ahead.
All right. Sorry if there's any background noise. Our dear Heavenly Father, we thank Thee for this wonderful school year that we are all able to meet together and to gain knowledge on the creation of our world and the wonderful way it works for our benefit. And we thank Thee for Mr. Riboldi and his willingness to teach us this year, and for the wonderful lessons he's given this year. Please help us all to have a good summer and to be able to meet back together in the fall. And I say these things in the name of Jesus Christ, amen.
Amen. Thank you very, very much. And thank you everyone for your participation. Have a wonderful summer. Okay?